Today we're going to talk about discrete versus continuous graphing. First, let's talk about discrete graphs. Discrete graphs are a collection of ordered pairs that don't allow for you to fractionalize the input values. Now, what does fractionalize mean? Essentially meaning that you can't break it apart, okay? So you can't have half of something, you can't have 2/3 of something, you can't split apart the input values, okay? Now, a pattern can be established to create additional points. However, this does not work if there is not a clear pattern. So although you cannot fractionalize the points, if there is a pattern, you can create additional points. But in general, we think of this as there are no in-between points. So with a discrete graph, you have specific, distinct, ordered pairs that cannot be split apart, they cannot be fractionalized. And then there would be no in-between points because of that. Versus continuous graphs, the given data points create a pattern that allow anyone to predict values that are not explicitly referenced in between the given values. The given data points create a pattern that allows anyone to predict the values that are not explicitly referenced that are in between the given values. So thus allowing us to fractionalize the information. Now, in the same situation as discrete, continuous, a pattern can be established to create additional points. However, this does not work if there's not a clear pattern. So in both scenarios, you might only be able to graph what you were given, but if there's a clear established pattern, you can find more points. But in general, continuous graphs, because you can predict values that are in between the given values, we generally think of this as in between values exist. So discrete graphs are specific ordered pairs, whereas continuous has a range of values in between given values that are provided. So values that are distinct and there's nothing in between versus ones that have values in between the given values. Okay, let's look at the images below to kind of get a vision of some functions, describing them as discrete or continuous. So thinking at the definitions of discrete versus continuous, the visualization on these graphs should hopefully help you establish those definitions a little bit better in your head. So remember that discrete is specific ordered pairs that we cannot connect because there's no values between them, versus continuous, meaning there's a pattern that can be established in between the values, thus having a connection between the points. So when we think about that and look at that, number one is going to be discrete. There's distinct points provided, okay, but there's no in-between points, okay? The points that we are given are the only ones that exist. So this would be discrete. Now, if we look at this one, okay, this one has values all ranging along this line. So at any point there is information all the way around, all the way up and down this graph. At any point, there's data. So therefore, this would be considered continuous. Take a second and identify the next two, what you believe to be true. Hopefully you notice that the images look very similar in how we establish them. Continuous has a connection and shows that there's a pattern between each pair of points, whereas discrete has specific ordered pairs that are separate and clear and separated from each other. And so that one would be considered discrete. So we talked a little bit about what it looks like on paper here with the graphs. Below, let's just fill in a little bit more information about what that looks like when we're graphing. I already talked about it. Let's put it here in definition. So graphing. When graphing, the potential ordered pair solutions, you will need to determine if the solution, or sorry, if the situation is discrete or continuous. When graphing the potential ordered pair solutions, you will need to determine if the situation is discrete or continuous. Now, how do we determine that? If discrete, you're going to graph the points so you can, and that would be either what is given to you or an ongoing pattern. But with discrete, you do not connect the points, okay? Because remember, distinct does not have in-between points, and you cannot fractionalize. So although we have distinct points, and there might be a pattern, we do not connect the points because there's no values in between. Okay? And so this compares with if it is continuous, you would graph the points that you can, and then connect them to show all the potential solutions in the situation. So although there are distinct points along, do that point. Although there are distinct points along the line, there's also little points in between every situation. Okay, similar to this one, there's distinct points, but there's also points in between. Okay. So therefore, obviously, you can connect the points. But for this one specifically, you also need to determine if it has a specific end point, or does it continue? Okay. And if something continues in math, how do we prove that? Or how do we show it? We show that show that relationship by drawing arrows at the ends. Okay, so again, if you look at here, we have arrows to show that this pattern is continuing. So again, when graphing, we determine if it's discrete or continuous. When it's discrete, we graph the points. We do not connect the points. Whereas continuous, we graph our points and we can connect them to show that there's data and points in between what we have. And for continuous specifically, you have to figure out, is what you have going to be an end point, as in like that's the last point, or does the pattern continue off the grid of what you've graphed? Okay, so going into question 2 and 3, the instructions say, for the following, title the graph, label both axes, and list numbers on both axes. Then create a table of at least 5 values that make sense for the situation. After, find the corresponding outputs, then graph each ordered pair. Lastly, determine if it is discrete or continuous and why. Okay, so let's look at number 2. Mr. DiCaprio works at the local movie theater. He's waiting to catch his break in hopes of being an Oscar-winning actor one day. He works in the fast lane at the concession stand that sells only combos. The small popcorn and large soda combo is $3.50. So the first thing you want to consider is, what two things are we comparing? Okay, so in this scenario, it doesn't give us all the information necessarily that we need, but it gives us a start of what we believe the situation is going to be talking about. Right, so we have these combos that are $3.50. Right, so the number of combos someone gets is going to be a situation, and that situation is going to be independent. Number of combos. Now, what would be compared in relationship to the number of combos? Well, it's going to be the total cost. So depending on how many combos they get, so let's say they're by themselves versus if they have their kids with them, or if there's a party or a group of friends, there's going to be a total cost for depending on how many combos they get. Okay, let's talk about what a function rule would be to represent this. So remember, we're going to start with f of x, and we want to consider, how does the numbers we have relate to what we are comparing? So we have number of combos and total cost. So remember, y is the same thing as f of x. So my total cost equals what? Well, what relationship is there going to be between $3.50 and the number of combos? Well, every time someone gets a combo, it's going to increase the amount of money. So therefore, 3.50 times x is going to incorporate that information. So every time I increase the number of combos, I multiply that to 3.50 or 350. Okay. Let's go ahead and start off with what we need to set up our graph. So first we want to title the graph. And you can title the graph anything you want. We could talk about how it is Mr. DiCaprio's work. You could talk about how it is the concession stand at a movie theater, lots of different things. Okay, but in reality, it's really talking about this fast lane purchases. Okay, because if the fast lane only sells this combo, this is what we're talking about. Now, when we're graphing, remember that horizontal represents the x values. So therefore, when I'm labeling my axes, x is going to be the number of combos, whereas my y value is going to represent my total cost in dollars. Okay. Now the next thing it says is to list the numbers on the axes. I'm actually going to hold off on that real quick because I'm going to first figure out what points I'm going to want to graph before I figure out how I'm going to number my lines, because I could number them by ones, I could number them by twos, fives, tens. As long as it's consistent, I can number it however I need. But let's figure out what numbers I need to have on my grid first. So if we're looking over here at my t-chart, I need to create a table of at least 5 values that make sense for the situation. Now, in this situation, does it make sense that I would have negative numbers? Am I going to have negative amount of combos? No. Okay. Am I going to have half of a combo? No. So I'm thinking about positive numbers. And again, who's to say that I don't go by myself versus have a group of friends? So, so let's say at least we buy one, okay? Because it wouldn't make sense if you went to the fast lane and not purchase this combo that's only sold on the fast lane. So let's say you just bought one. Okay. Well, 350 times 1 is going to equal $3.50. Now, you can pick whatever numbers you want here, but keep in mind, obviously, the bigger they get, the harder it is to grab. So you could simply just say, well, let's figure out what happens when I buy 2, 3, 4, 5 of these combos. Okay, so take a second and fill out what would happen if I buy 2, 3, 4, 5 combos, share your work, and figure out what would be our outputs given these inputs. Okay, so once you figure out the work, you should get the answers of $7 or $10.50, $14, and $17.50. Now, when we're thinking about how are we going to graph these numbers, you have to that you're not just going to just be able to plot just those points alone. Okay. It's not realistic and it's not reality that I would just simply put 357 and so forth. Sometimes you have to approximate your values. Okay, and so I need to get all the way up to 1750, okay, on my total cost. Now, if we count our number of lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I can't just go by ones, okay, because I won't make it. Okay, so the next smallest I could go by is twos. So starting in the corner, we know is 0. Okay, so then I'm going to go 2, 4, and all the way up. And to clarify, this is the lines, okay, not the spaces, the lines. And if I go all the way up, okay, we get to 24, which is enough to show my data. Okay. Now we need to figure out the number of combos. Now, we only went to 5 combos, okay, but if I only go 1 through 5, my graph is going to be this small version of my grid. Okay, so instead, I'm going to go ahead and space out my numbers. So as long as I'm doing the same spacing along the side, I'm good. So if I'm going to skip every other line just to give a little bit of space in my graph, then I'm going to say I'm going to buy 1 combo, 2 combos, and I'm going to skip every other line. 3 combos, 4 combos, 5, 6, 7, 8, 9, and 10. Now I only went to 5, but I have space until 10. Okay, so I have titled, I've labeled my graphs, I've numbered my, I've titled my graph, labeled the axes, listed numbers on the axes, created my table. Now I need to plot my points, okay? So at 1 combo, we spent 350. So I'm going to approximate 350. Okay, so it's going to be right about here. Okay, and then at 2, we have 7. And 3, we have 1050. At 4, we have 14. Oh, that's one exactly right on the point. And at 5, we have 1750. Okay, now there's a clear, distinct pattern. If I wanted to make more points, I could. But you can just stick with the 5 points that you graphed. Okay, now from here, now that we've plotted our points, we want to consider, is this going to be discrete or continuous? So the main thing when you're considering discrete versus continuous is discrete is specific points, whereas continuous, I would connect with a line saying that there's data in between the points that I found. Now, again, we want to think back to the definition we wrote on the front. Can I fractionalize my points? Can I find 1.5 for an x value? Could I find 2.3 of an x value? And in this case, the answer would be no. Can I buy 1.5 bags of popcorn with half a soda? No, it doesn't work that way. Either buy one combo or two combos. You can't split up a combo. So therefore, this one is going to be discrete. And you remember B/C stands for because you can't have, or I can say, shouldn't say have, you can't buy half a combo. Okay, so therefore this would be all I have on my graph, no connection, just that alone. All right, let's go ahead and look at number 3. All right, number 3. Joan has a bad reputation for riding jets to concerts around the country because she loves rock and roll. She finds out ticket starts at $120, but goes down in price $5 for every empty seat on the jet. Okay, so let's figure out what two things would be compared here and what is a function rule. So rereading the scenario, we know that a price of a ticket goes down $5 for every empty seat on the jet. So every time there's an empty seat, it goes down $5 more. That's going to indicate that that's something to do with our independent variable. So number of empty seats is going to be in direct relationship to what? It's going to be a direct relationship to the cost of the ticket. Because that cost depends on how many empty seats you have. Now, go ahead and think about what we would do to incorporate 5 and 120 to create a function rule. So let's see what you did. Now, f of x equals, now we know that the price goes down $5 for every empty seat. So if it's going down, that means I'm going to be subtracting $5 for every empty seat, meaning I'm multiplying that to x. Now, what does the price start at? Well, the price starts at 120. So therefore, I'm going to add 120. Okay. You could also write this as 120 minus 5x as well. That also works. Keep in mind that typically in algebra, we always write the variable first, but in cases where we're subtracting, these also work when you're thinking about taking away from the original 120. Now, the next thing we need to do is title our graph, label our axes, and then we'll figure out what points we're going to have, go back and number, plot our points. Okay. So let's first talk about naming our graph or titling our graph. Okay. So again, thinking about what we're comparing, what we're finding. Okay. So we can figure out costs of tickets. You could be more specific. You could say Jones ticket prices. Okay. But this is really what we're comparing. We're comparing the cost of tickets. And remember, our x, our independent, is always our horizontal. So number of empty seats. And that's being compared with the cost of the ticket. Okay. And again, going back to what I said in the last problem, we do need a number, but let's first figure out what points we're planning on plotting before we actually number anything. So when we consider how much the ticket costs, okay, is it likely that I could have 0 empty seats? Have you ever been on a full flight? They're not necessarily fun because you don't get that extra elbow room sometimes. So let's say there's 0 empty seats. That's an option. Okay. Now, as far as what values I pick from here, remember, you can pick any values. There doesn't have to be a pattern as long as they're just increasing. So I can't say 10, then 5, but if I wanted to say 5, then 10, that's perfectly okay. It really doesn't matter. But let's say we're going to pick a range of tickets. So let's say maybe it's a slightly empty flight. There's a couple seats missing. Okay, maybe even 4 tickets. Sorry, 4 seats are empty. Okay. But isn't it possible there's a lot of seats missing? Let's go ahead and jump up. Let's say there's 10 empty seats, or even maybe 16 empty seats. Okay, now there's not necessarily a distinct pattern between these points. Okay, we don't have to. We're just saying, hey, these are potential points that make sense for the situation. Okay, we could have a full flight, a fairly full flight, or maybe we have some empty seats in there, some extra wiggle room. Go ahead and figure out what the price or the cost of ticket would be when we consider those amount of empty seats. Go ahead and show your work over here to the side. Okay, so if we look at the work, we should get the values of 120, 110, 100, 70, and 40. Okay, really like that $40 ticket price. That sounds wonderful. Right, and so we show that we multiplied -5 times the x values and then added 120, and we get these values. Now, looking at the numbers that we are graphing, we need to get at least to 120. Okay, does it matter if I go over? No, because the most I'm ever going to spend on a ticket is 120 bucks. Okay, which is great. Not realistic in today's market, but let's say she's got a great deal. Okay, so the most it's ever going to cost is 120. So I need to make sure I at least get to 120. So again, let's count those lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 lines. If we have 12 lines and we have to get to 120, what am I going to have to go by? Well, 120 divided by 12 is 10. So that means each line is going to have to be 10. So I'm going to go ahead and go by tens. And again, we're going on the lines. And I will make it to 120. All right. Now let's talk about empty seats. Okay, we want it all the way to 16. Okay. But let's make sure we could actually go to 16 looking across. Now let's count how many lines we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, I have 20 lines, and I only need to get to 16. Okay, so I could go by ones. But would I skip around like I did here? Sorry, not skip around. Skip every other line, I meant to say. No, I don't want to, because if I skipped every other line, I wouldn't make it. So I'm just going to go by ones. Now, to save myself, sorry, to save yourself time, even though I'm not skipping lines, I could just number every other line with my evens. So rather than writing 1, 2, 3, that might get a little busy, okay? I could just simply put 2, and rather than writing every number, let's say that's 5, this would be 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so I didn't skip lines necessarily because each other value is going to be worth 1. Okay. But it just saves a little bit of space of having to write sideways, okay? Writing vertically works really nicely because each number has its own line. When you're writing horizontally, it kind of gets a little jumbled up there. So even though I didn't write the number, this line would still be 1. Okay. Now let's plot those points. So at x equals 0, my y value is 120. And then at 2, we have 110. At 4, 100. At 10, we went down to 70. At 16, we went to 40. Now, I specifically picked points that jumped around a little bit, right? Because we have to consider there'd be a lot of empty tickets, or sorry, a lot of empty seats. Now, would I be able to figure out a pattern going on in between these? Yeah. If you notice, for every 2 tickets, it goes down $10, which makes sense. $5 for 1 seat, $10 for 2 seats. So I could figure out points in between here to plot more points. Do I have to? No, not necessarily. I can just keep the 5 points that I have. Okay, now the last question we need to ask ourselves is this discrete or is this continuous? Go ahead and think about that question. Okay, so what do we think? Discrete or continuous? Can I put points in between these? Yes, I could technically plot more points if I wanted, but would I be able to put points consistently by drawing a line? Because if I draw a line that says, hey, at half of X, I would have a price. At 1.5, I would have a price. Is that realistic? Would I have a price when I have 1.5 or 2.4? Can I have half of a seat? No. Right? And so you might have thought, well, hey, this has to be continuous because we already did discrete. Well, I accidentally messed up and I gave you 2 discrete options. This one is discrete. Because much like you can't buy half a combo, you can't have half of a seat. Okay, so to finish up, let's talk about a direct relationship between discrete and continuous to give us a little bit of a better example of what would be a continuous situation versus a discrete situation. So I'm going to flip back to the front. Okay, remember that discrete is specific given points. So let's say, okay, we're thinking about a grid. Okay, let's think about a situation where you are measuring water. Okay, so if I'm measuring the amount of water, it's going to depend on what type of water I'm measuring. Now, if it's discrete, it has to be specific numbers. So that would be like measuring the number of water bottles. Okay. You can't have half a water bottle. Now you could drink half a water bottle, but if you're measuring the amount of water, if you have 1 bottle, you're going to have a certain amount of water. If you have 2 bottles, you're going to have a certain amount of water, and so forth, right? But I can't say half of a bottle. Whereas continuous, let's say, again, I'm measuring the amount of water. But in this case, let's say I'm getting amount of water from a sink. Okay. If I'm putting the faucet and turning it on, am I going to have distinct amount of water? No, I'm going to have water that is continuously growing. Okay, because if I'm filling for so many seconds, the water is constantly flowing in a sink or from a faucet. So I'm constantly going to be growing the amount of water because it's continuously flowing. The water from the sink is always flowing, whereas the number of water bottles is going to be a distinct amount of points. Okay, and so here's a nice little description of showing if I had the number of water bottles versus the amount of water from a sink flowing, okay, or the seconds of water pouring from a sink. So this is the end of our notes, and good luck on your assignment.